Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over VSEPR theory and how to use it to predict the molecular geometries of molecules and ions. So the first thing you need to start with is your Lewis dot structure. So I'm not going to go over how to do that in this video. If you know how to do your Lewis dot structures correctly, great. You're going to have to write a correct Lewis dot structure and then use that to predict what the molecular geometry is or the electron geometry. So I've took the liberty of writing out the Lewis dot structures that you should get if you know how to do that. If you don't know how to do your Lewis dot structures, then go back to another video. I have a few videos on how to do Lewis dot structures. So once you have your Lewis dot structure, and you know it's correct, now you can figure out what the molecular geometry is going to be. So I'm going to talk about the electron geometry and the molecular geometry to compare the two. So when you are looking for your electron geometry, the electron geometry, you're looking at all of the electron groups, bonding and non-bonding. So here I have 3 bonding groups and 1 non-bonding group, 1 lone pair. So I have a total of 4 groups, 4 electron groups. That tells me that the electron geometry, I'm going to say EG for electron geometry, is going to be tetrahedral because that's the electron geometry you get when you have 4 total electron groups. So it's going to be tetrahedral. Okay, the molecular geometry, the MG, molecular geometry, that's only based on bonding groups, on bonded atoms. So I have 1, 2, 3. And so I have 1 lone pair, but I have 3 bonding groups. So that means that's going to cause these bonds to get closer together. So if you are familiar with the shapes, or if you use a table, you can look on your table. You would look on the table for 3 bonding groups and 1 lone pair. So, and the total number is 4 groups. In that situation, you have a trigonal pyramidal shape or molecular geometry. So this is going to be trigonal pyramidal. Okay, so it's trigonal pyramidal. So that's the shape of the molecule itself. The electron geometry is tetrahedral. These two are different because you have lone pairs. If you did not have a lone pair, if this was instead an atom, then the electron geometry and the molecular geometry would be identical. Since you have a lone pair, they're not identical. And also the bond angles are not going to be ideal as well. So if it was tetrahedral, we would say that the bond angle is 109.5. But since you have a lone pair there, the lone pairs take up more space. They have more repulsive power. So therefore, they're going to push the other atoms closer to each other. So this is going to be less than 109.5 degrees. So this we would expect to be less than 109.5 degrees. So like ammonia, phosphorus is in the same group as nitrogen. So we might expect this to be probably close to 107 degrees. Okay, so that's problem number 1. Problem number 2, we have ICl4 minus. This is an ionic, a polyatomic ion. So here, this is the way I drew it. I have my 4 chlorine atoms bonded to my iodine. My iodine is the central atom. And so you'll notice there are 2 lone pairs on the central atom iodine. So the total number of electron groups is 1, 2, 3, 4, 5, 6. So I have 6 total electron groups. So if you look on your table or if you have it memorized, you know that if you have 6 total electron groups, that's going to give you an octahedral electron geometry. So the electron geometry here is going to be octahedral. So you have an octahedral electron geometry. Your molecular geometry is going to be different. So for the octahedral electron geometry, we would expect 90-degree angles. But here, because we have lone pairs, the lone pairs are going to take up more space, so these are going to be pushed closer together. So the angle you would expect of 90 degrees is not going to be here. It's going to be less than 90 degrees. So these are going to be more pushed together. So with that, this is going to be the shape. Now, the shape that you're going to get for this, again, if you look at the table, then you should be able to look up 6 total electron groups. 4 of them are bonding, 2 of them are non-bonding, and that should give you the shape. And that will give you seesaw shape. So the shape or the molecular geometry for this polyatomic ion is going to be seesaw. Okay? Again, it's seesaw is if you rotate it this way 90 degrees, then it looks like, here's the children on the seesaw, and you can go like this. So seesaw shape. So that's the second one. And again, the less than 90 degrees. So the angles here, again, ideally for an octahedral electron geometry, 90-degree angles is what you'd expect. But since you have lone pairs, it's going to be less than 90 degrees. So less than 90 degrees. Okay, what about the next one? So the next one is this CLNO. So how do you figure out your central atom? Your central atom is the one that has the lower electronegativity. It's also the one that has the most unpaired electrons in its Lewis dot symbol that we learned. So nitrogen is going to be the central atom. So when you do your Lewis dot structure, you'll notice I have a double bond here, I have a single bond, and I have a lone pair. So in this case, the electron geometry is, again, counting all electron groups. The double bond is 1 electron group, not 2. The single bond is another electron group, so that's 2 total. And then the third electron group is the lone pair. So I have a total of 3 electron groups. Whenever you have 3 electron groups, your electron geometry is going to be trigonal planar. So your electron geometry is trigonal planar because I have 3 total electron groups. However, because I have 1 lone pair, if I look on the table, or again, if I have it memorized, if I have 2 bonding groups and 1 lone pair, then that means that the molecule itself, the atoms themselves, are bent. Now, you could draw it like this, and students will make a mistake and they'll see this and they'll say, oh, it's straight, it's linear, it's a 180-degree angle here. You're making a mistake there because you're looking at the Lewis dot structure as if the Lewis dot structure is meant to give you the actual picture and shape of the molecule. That's not the purpose of the Lewis dot structure. The Lewis dot structure, I can draw like this. This looks like 90-degree angles here, but they're not 90-degree angles. They're not even close to 90-degree angles. So don't let the Lewis dot structure fool you with regard to the bond angles. You have to know what the bond angles are based on the table. So either you need to memorize it, get it in your head, or use the table if it's given to you to use. Usually professors don't, or teachers don't give you the table, and they expect you to know it without the table. So make sure you know what you need to do. So here, since I have 1 lone pair here, this lone pair is going to bend these closer together. I have a trigonal planar situation going on here, but the atoms themselves are going to be bent. So the molecular geometry is going to be bent. So that's the molecular geometry. Now finally, what about problem number 4? So here, I have three iodine atoms bonded together. Let me fix this. There you go. So I have three iodine atoms bonded together. I have one as my central atom, and you'll notice that in the central atom has three lone pairs. Now, if I want the electron geometry, I count all the electron groups around. So I have 1, 2 bonding groups, 1, 2, 3 lone pairs. So that's going to be 5 total. So we learned before, if you ever have 5 total electron groups around your central atom, then the electron geometry is trigonal bipyramidal. So trigonal bipyramidal is your electron geometry. So let me put that down. So trigonal bipyramidal. Okay. So that's your electron geometry. Now, remember that for the trigonal bipyramidal shape, the trigonal bipyramidal has 2 different angles. You have the equatorial angle and you have the axial angle. And so remember, the axial angles are between what's at the axes, right, and what's on the equator. If you're thinking the central atom is a globe or the Earth, you have the equator, and so these lone pairs are on the equator. Why are they on the equator? Lone pairs are on the equator or the equatorial position because they need more space. And if you remember, the equatorial position allows for 120 degrees of separation from each other, whereas the axial positions only allow for a 90-degree separation. So remember that the lone pairs are larger, they're more repulsive, they want more space. So if you have a lone pair and you have an electron geometry of a trigonal bipyramidal, those lone pairs go in the equatorial position. They do not go in the axial position. Okay, so here we have our 3 lone pairs in the equatorial position. We have our 2 bonded atoms in the axial positions. And so you'll notice that, again, the axes are directly opposite from each other. So this is a linear molecular geometry. So the molecular geometry is linear, right? And so this is going to be in 80 degrees. 180-degree angle in this molecule. Okay, so that's it for these examples. I hope this helps you figure out like how to predict the molecular geometries and the electron geometries and how to know the difference between them. If you like this video, share, like, subscribe. So hit the notification bell to get notified of any other videos. Hit the subscribe button. Like the video, and if you have any questions or if you want me to cover anything else, make a comment in the comment section. Thanks for joining me, and I'll see you next time.